Perfect, recording in progress. Verstanden. Yeah, so once again, the title of my talk, Reduce, Dissolve, Precipitated, the Multiple Effects of Early Diagenesis on Sediments and Sedimentary Rocks. I guess summarizes in a nutshell the type of research I generally do. And I should say I am, yeah, my background is in sedimentology, but really I would say in terms of methods, I still look at sediments, but I mainly apply inorganic geochemical methods to understand what makes the sediments tick, basically. And yeah, as was already mentioned by Thomas, I've spent some time on research ships, for example. It's always nice to show pictures of ships, I guess. So here on the left, you see the JOIDES Resolution. I've been on her twice. And some of you might have heard the news that very sadly, this ship will go out of scientific service at the end of next year. So that's a bit of a blow to the general IODP program, but we'll see. Let's stay positive that good things are still to come. And then I also spent quite a bit of time on the Polarstern here on the right. That was my longest expedition, 10 weeks in the Central Arctic Ocean. And I'm showing these two ships because some of the data and some of the records I'm going to show come from or were obtained from these ships. So let's see, how do I click on? So it won't move to the next slide, why not? Here we go. Sorry about that. Okay, so my talk is mainly going to be about early diagenesis. So what does early diagenesis mean? That's just a bit of an introduction for people who don't tend to think about early diagenesis all that much. It's basically changes in the chemical makeup of sediments at relatively shallow depths. So you see this schematics illustration on the right-hand side that goes down to roughly 10 meters, but early diagenetic processes can also happen at greater depths. As a rule of thumb, I guess the greater the depth, the less diagenetic overprint you find. And at some point, high temperature and high pressure take effect, and then you're moving into what I would call the later stage diagenesis. But it's kind of a, I guess it's a fluid transition, and I'm not sure it's all that well designed. But I don't want to stay with definitions for too long here. One thing that's important to say is early diagenesis affects all aquatic sediments, lakes and marine sediments alike. And very often the processes of early diagenesis are related to the degradation of organic matter. And this happens by microbial communities. They are very nifty little buggers. They can pretty much use whatever is available to well, basically catalyze chemical reactions that provide them their metabolism with energy. And they usually do this using a range of electron acceptors that is shown here in the middle panel. So first you start with organic matter degradation using oxygen, then nitrate, manganese and iron oxide, sulfate. At some point they ferment methane. That's the standard so-called catabolic sequence. And in the process, and that's really the most important bit for sedimentary geologists, certain minerals get dissolved, new minerals get precipitated. So what happens is you have a redistribution of certain elements within the sediment column. That happens sometimes really long after sediment deposition. And obviously, interpreting the sedimentary record, you always have to have this potential early diagenetic overprint in mind. Now, this is just to quickly show or say, if you're only dealing with the chemical elements, aluminium, titanium, zirconium, rubidium, potassium, sodium, you don't have to worry all that much about early diagenesis, and you can just log out again. But in reality, if you're using geochemistry as a tool in interpreting the sedimentary record, a lot of commonly used elements are partly very strongly affected by diagenetic processes, sometimes even completely controlled by diagenesis. And this affects, for example, iron, manganese, calcium, magnesium, often bound to carbonates, barium sulfate, phosphorus, many trace metals. So a whole bunch of elements. And here on the right-hand side, you see hardly diagenetically precipitated iron and manganese oxide layers in an Arctic sediment core. And this is one of the case studies I'm going to deal with in the coming half hour or so. And this is just a slightly different illustration of how this catabolic sequence looks like. And this was introduced by Canfield and Tamdrup in 2009. And I think the title of this manuscript was called something like "Why We Wish the Term Suboxic Would Go Away." Basically, they suggested to list the catabolic sequence rather in the order of different metabolic processes or main electron acceptors that are being used, and not so much with the, let's say, availability, abundance of oxygen. So it's really the same thing that I showed earlier, just with a slightly different touch, I guess. But here on the right-hand side, I did some columns that show what kind of minerals you would dissolve or precipitate in the different diagenetic zones. And you can see on the dissolution side, for example, you have at a certain depth the dissolution, sometimes the complete dissolution of manganese and iron oxides, and slightly higher up in the sediment column, they reprecipitate again. So you really shift these elements around, and sometimes the color changes that are associated with them. You also have changes in carbonate minerals. And one zone I want to specifically focus on is this so-called SMT, which you can see in the middle panel, the sulfate methane transition. And that is basically where upward diffusing methane meets downward diffusing sulfate. And in this zone, you have a whole bunch of diagenetic processes occurring. I'm gonna show you a few examples in the forthcoming. So now, as a very general question, what controls the degree of diagenetic overprint, early diagenetic overprint? And there are a few main players here. I'm just going to go through them a little bit. So because early diagenesis is often driven by organic matter degradation, the amount and reactivity, so what type of organic matter is supplied to the sediment, really determines how much diagenetic processes you have going on. A lot of algal or bacterial organic matter, that really triggers the microbes, and you have very strong diagenesis. If it's mainly chopped up plant debris, maybe not so tasty for the microbes. Then oxygenation of the water column plays a big role, because that first of all determines, is this most efficient electron acceptor oxygen available? And if it isn't, that can lead to this catabolic sequence basically migrating out of the sediment and into the water column. That's something, for example, that happens in the Black Sea right now. And that is also kind of linked to this, what it says here on the upper left, the availability of electron acceptors other than oxygen. Obviously, if you have no oxygen, that's a big thing. And there were certain periods during Earth history, very long periods, in fact, where there was no oxygen in the ocean whatsoever. But then also the supply of other electron acceptors, and I'm mentioning sulfate here, for example, can determine how strongly diagenetic processes overprint the sediment and what kind of minerals you form. And obviously, that also generates differences between what you have in lakes and what you have in marine systems, because in lakes, you tend to have much less sulfate. And then one really key parameter is the sedimentation rate. And I'm going to show in the forthcoming slide how sedimentation rate actually matters. Long story short, if you have very high sedimentation rates, organic matter gets buried quickly, and you're basically reducing the degree of diagenetic overprint that every individual sediment layer experiences. And this is kind of shown in this slightly busy slide, but I'm going to guide you through it real quick. Changes in sedimentation rate or in the input of organic matter, or changes in the availability of electron acceptors, they define whether your diagenetic system or geochemical sedimentary system is in steady state or in non-steady state. Basically, if it's in steady state, and that means if all external parameters that I just listed are unchanged during deposition, then the diagenetic processes affect all sediment layers equally. So there will be changes to the geochemical makeup of the sediment, but they are unlikely to lead to any significant element or mineral enrichments or depletions. And this is what is shown on the top right here on this panel, where it says before elastic glaciation. This is basically an example of a study we did on the Zambezi shell, on the Zambezi continental margin. You have a core from a deep sea fan, and when sea level is low, it gets lots of sediment. It basically bypasses the shelf, lots of sediment, high sedimentation rate. So the diagenetic zones move through the sediment really, really fast. Now, what happens then is if any external parameters change, and in the case of the Zambezi fan, it was the sedimentation rate, then the diagenetic zonation in the sediment can be fixed. So dissolution or precipitation reactions have a lot of time to generate strong diagenetic signals and significantly overprint the record. And this is basically what happened on the Zambezi fan. After the elastic glaciation, the sea level rose. As soon as it started flooding the shelf and generating more accommodation space on the shelf, basically the deep sea fan was sediment starved. Very low sedimentation rate, and that means the diagenetic zonation in the sediment in this lower picture, most notably around this sulfate methane transition, really generated strong diagenetic signals, including a loss of magnetic susceptibility as you are dissolving iron oxides and precipitating pyrite, for example. You can then also precipitate orthogenic carbonates, leading to abnormally high cementation, lithification of certain sediment layers, and so on. Various things can happen if the diagenetic zonation gets fixed. Now, one question that obviously arises is, are only geochemical parameters changed by geochemical processes? Well, it's quite an obvious answer, no. Also, physical properties and biological properties can be impacted, and this is really not based on my own research so much. It's more of a bit of an overview, so that I certainly mentioned these things. So you can obviously have the dissolution of biogenic carbonates and the precipitation of orthogenic carbonates, and there are some examples here at the top. So you have an ODP, IODP sediment core, where you have an abnormally lithified layer of orthogenic carbonate that wasn't there when the sediment was deposited. It precipitated within the sediment column, and in this case, it's ferro and dolomite. You can sometimes also have these in this outcrop, these stringers, basically these lenses, these nodules, sometimes continuous beds of orthogenic carbonate. You can also obviously have them as coatings on foraminifera, for example. That's the carbonate side. Then you have the silica side. So opal, amorphous silica, volcanic ash, biogenic silica dissolves, and that can lead to various types of precipitates. You can form orthogenic clay minerals, and you can also precipitate at a later stage chert layers and chert nodules. And there are some examples again from the IODP core, but then also from the English chalk coast, where you see this carbonate-rich material, this chalk with these interbedded chert layers. You can also have transformations of organic phosphorus, in fish bones into orthogenic apatite. So here you change the mineral phase a little bit, and then again this abnormal cementation and lithification. And this is again a slide where I've tried to summarize some of the things that will happen in such a diagenetic sequence, schematically shown on the left, in terms of mineral dissolution and precipitation, and what that might look like in a sediment core or in an outcrop. So I'm focusing again on the sulfate methane transition. You're dissolving iron oxides, and you're precipitating iron sulfides, and you have here on the right-hand side magnetic susceptibility that really just goes down like crazy. Has nothing to do with the original input of iron minerals. That's a purely diagenetic signal, and you can also see that in the in these different iron fractions I'm showing here that show basically iron oxides are almost completely gone. And then in this zone, you can also precipitate calcium or magnesium carbonates, and you can see if you'd pick foraminifera from this core, you would certainly get rather the case of picture C, which has a very strong orthogenic carbonate overgrowth and not this nice glassy preservation of picture A, or you would even get these crazy big dolomite or carbonate nodules. And then one thing I wanted to mention is, I said dissolution of opal, of amorphous silica. That is a process that is happening, but it's unrelated, interestingly, to organic matter degradation. That's a largely abiotic process. It's simply because volcanic ash or amorphous material is quite easy to dissolve. And here are some examples in the left bottom corner, where you see diatoms that are slowly getting dissolved and basically precipitating orthogenic clay minerals on their surfaces. And you can see this in, for example, pore water profiles in the silicic acid concentration. Now, one thing that I work on quite a lot to understand diagenetic processes and diagenetic effects are pore waters. So pore waters you can extract in various different ways from the sediments. The top picture is me extracting pore water on the Joyous resolution using a hydraulic squeezer, basically, a press. You can also use a more gentle method for more water-rich sediments using these rhizome samplers, artificial like mini roots you insert into the sediment, and that they give you the pore water. And you can learn a lot from the composition of these pore waters. You can identify diagenetic processes or the zonation in the sediments. The only caveat is these profiles provide a snapshot of the biogeochemical status of the sediment when you sampled it. And they can't tell you what diagenetic processes might have occurred in the past. So it's good for signposting the diagenesis is affecting the sediment, but it's not this silver bullet that basically tells you exactly how to subtract the diagenetic signal, sadly. But we might get there towards the end of the talk. There are other ways you can use. And now I wanted to go through two case studies that exemplify some of my work. The first case study is dealing with manganese-rich layers or iron and manganese oxide-rich layers in the Arctic Ocean. So this is something that I've been working on for the last 10 years or so. And the background is basically in the Arctic Ocean, people are interested in understanding how the Arctic Ocean functioned during past periods of global warmth, let's say interglacials. The problem is it's very, very difficult to pinpoint interglacial intervals using standard dating methods in the Arctic Ocean. You have lots of different dating problems for the various reasons I list here. Basically, almost none of the conventional marine sediment dating methods work. But then some people found, oh, there are these cyclic brown manganese-rich layers that they occur all along the continental margins of the Arctic Ocean. And they always look the same. They seem kind of cyclic. Why don't we just count manganese layers? Now, there are certain alarm bells ringing when manganese layers are supposed to be correlated, because manganese is one of the diagenetically most mobile elements. But this is just to show how the people in the 80s and 90s went ahead. They identified these in this middle picture here, these so-called brown beds. Often they are associated with certain grain size changes, and sometimes also with a certain ichnofacies. And they basically use them to generate an Arctic stratigraphy and to correlate glacial interglacial cycles across the entire Arctic Ocean. And in 2000, there was a first attempt to correlate this Arctic manganese stratigraphy to this low latitude Delta 18O stack generated by Bassineau in '94. This basically linked the Arctic into the global oxygen isotope stratigraphic framework. So far, so good. People accepted that. And then I looked into this to an extent triggered by some questions by Rüdiger Stein from Alfred Wegener Institute about these manganese-rich layers. And I looked into the literature and I found that already in the 60s, people had shown using pore water data, which you can see here in this middle slide, that clearly show there is a lot of manganese redistribution happening in these sediments. And they already interpreted these records in terms of diagenesis. So you have here on the left-hand slide, you can see you have a manganese peak that exists, but it's not very high. It's this lowest peak, and that is associated with a peak in pore water manganese, which means pore water is enriched in manganese. That can only happen if manganese oxides dissolve. And then the manganese diffuses away, usually, well, to below to form carbonates, probably to the top to form a new manganese oxide peak. So you're really shifting the manganese peak. It might disappear entirely from the underlying sediments and migrate to the shallower sediments. Somewhere in the middle, you have this relict manganese oxide peak, which seems to be currently unaffected by diagenesis, but will probably be affected later. So there are these two opposing views. Basically, yeah, well, I'll just skip over that. It's too much text. Sorry about that. But basically, to reconcile these different views of marine geologists and biogeochemists, I guess, over the last 10 years, I've worked together with quite a few colleagues to understand why and how these diagenetic, the diagenetic processes and the stratigraphic record might be reconciled or married in a sensible way. And yeah, I'll show you in a minute what we found. But first, I wanted to go through our process of how we try to understand how in these Arctic sediment cores the manganese layers are actually being redistributed or not. So the pore water data I showed you before were generated in the 60s. This is from a much newer study that we published from a central Arctic Ocean sediment core, roughly 8 meters long. You can see on the left-hand side, manganese peaks everywhere. And interestingly, these manganese peaks are always associated with enrichments in other trace metals like molybdenum and cobalt. These elements just love to absorb to manganese oxides. It's the same for manganese nodules you find on the Central Pacific seafloor. Now, one thing we spotted was that the enrichments of these trace metals aren't always uniform. So can that tell us something about what has happened to manganese in the past? Well, we analyzed pore waters once again, and you can see on this top left slide, first, there is very little sulfate reduction going on. So the sediments are diagenetically, well, largely in the oxic range, I would say. But then you have a lot of manganese diagenesis going on. Really a lot of manganese being pumped into the pore waters by manganese oxide dissolution. And then you look at the molybdenum, which is the third line here. There is also a lot of molybdenum remobilization into the pore waters. And then you look at cobalt, nothing. We still don't fully understand why that's the case, but basically, as manganese oxide layers get dissolved, molybdenum goes with the manganese, but cobalt doesn't. Cobalt stays behind. And that now allowed us to look at molybdenum-cobalt ratios within these layers and define layers that have experienced the diagenetic loss of manganese and the diagenetic addition of manganese. And we've applied this to various cores in the Arctic Ocean, and that gave us a pretty good handle on what happens in these sediment cores. And it also allowed us to generate a relatively generalistic picture of what the Arctic Ocean might have looked like. So this is what, let's say, a cold phase in the Arctic Ocean looks like. You have almost year-round sea ice. You have probably very little sediment coming in, probably delivered by saline brines from the shelf. And low sedimentation rates, once again, means the diagenetic phase, the diagenetic picture in the sediment stays the same. So you have some schematic pore water profiles on the right, and you can generate a manganese-rich layer in the sediment without any bioturbation. It's a layer that forms in the sediment, maybe in a meter or 2 meter steps, who knows. So that's a manganese layer you could form in the sediment. Then melting starts and interglacial starts, and then all hell breaks loose. You have a lot of input of metals, iron, manganese, other trace metals from the continents. You have higher primary productivity, so a lot of organic matter arriving at the seafloor. And that basically means you're generating a superficial brown layer at the Arctic seafloor that is then also strongly bioturbated. So that means you can generate two different types of manganese layers in these Arctic sediments. That was our concept. And a few years later, we even found these different types of layers. So the left-hand core here is from the Alpha Ridge, which is one of the most ice-infested parts of the Arctic Ocean. And you can see these interesting dendritic structures. Here, manganese oxides have basically been added diagenetically to the sediment, and you're generating a manganese layer that is unrelated to depositional processes. And most, I have to say, of the manganese layers show this very strong bioturbation, and that's a picture here on the right. It doesn't tell me very much, but I was working with Ludwig Löwemark, who is an expert in ignofascies, and they are very pervasively bioturbated by different types of organisms. So really the degree of bioturbation or the lack or presence of bioturbation can tell you a lot here. Now, case study 2, and I'm going through this quite quickly. This is about barium as a paleoproductivity proxy. The idea is we want to reconstruct primary productivity and carbon export through Earth history. That's a thing that's really essential to understand the carbon cycle and climate. Now, biogenic barite has been found, or is assumed, to be produced in the water column within sinking organic aggregates, and it accumulates with organic matter at the seafloor. The first finding of this was in the North Pacific or Central Pacific. So the apparent solution then is, okay, let's measure enrichments of, let's say, biogenic barite or excess barite relative to the detrital background. And that shows us high productivity events, and it seems to work well for certain environments. For example, in the Southern Ocean, this is an example from the North Pacific, in fact, where you see these really nice barium layers. It also works for Mediterranean sapropels. But you have one problem with barite, and that problem arises at this sulfate-methane transition. Biogenic barite is not preserved in marine sediments if the pore waters are sulfate depleted, because it's a barium sulfate. If there is no more sulfate in the pore waters, that stuff gets dissolved. So you're losing this productivity signal. And then barite reprecipitates, it dissolves, the dissolved barium diffuses up, meets sulfate again, just above the sulfate-methane transition, reprecipitates as diagenetic barite, and it forms an orthogenic barite front. And that is just geochemically very hard to distinguish from biogenic barite. And one of the main problems is, ironically, in fact, pore waters are usually sulfate depleted when organic matter export, so productivity, organic matter arriving at the seafloor, is very high, which means in very productive systems where we are quite interested to understand how much was actually coming in, we often cannot reconstruct it using the barite proxy. So for example, here in this case, dealing with Cretaceous black shales, but it also happens at methane seeps, for example, where you also have very steep biogeochemical gradients. And this is an example from some own work, a PhD student of mine from the Gulf of Alaska. You see on the left-hand side, the methane profile in red and the sulfate profile in blue. And you see sulfate is depleted at some point, methane increases at some point. You seem to have a massive gap in there. We don't understand why. And then on the right-hand side, the red dots show barium in pore waters. So what we see is barite is indeed dissolving, and barium is being released into the pore waters. So you're losing definitely the primary productivity signal. And you see that you are forming certain diagenetic fronts. So the brown line on the right hand shows barium peaks basically. And that's the sulfate methane transition zones. You form, certainly at this lowest one, you form a pretty massive barium peak. So that's an orthogenic enrichment. If you just did XRF core scanning, you would probably say, oh, look, there's a high productivity event. But it's really not the case. And then you have these other barium aluminium peaks, and they certainly have potential to identify past positions of the sulfate methane transition zone, which is really quite a critical and interesting zone in terms of marine biogeochemistry. So, okay, we know there is this barium diagenesis going on. Can we solve this problem somehow? You can, in certain instances, if you're lucky and if you have the right kind of data, by combining pore water and sediment geochemistry with reaction transport modeling. And that's something that we did, led by Laura Wehrmann, in the Bering Sea, where it's a very highly productive part of the world ocean. And I'm showing here the sulfate profile, and you see sulfate goes down, and then it has this strange bump. It never goes down to zero, but it has this, yeah, roundish pattern. And then you look, and that's something weird in the first instance. We didn't really understand why that's the case. And then this low sulfate interval also is depleted in barite. Well, actually, the barite is depleted a bit further up. So that already indicates you probably had barite dissolution at some point in sulfate-free pore waters. And you also have a really massive orthogenic barite layer. The data shown here don't actually show the barite layer. That consisted really just of barite. You had that above this interval. So how can we explain this? Now, what you can basically do is, and I'm not an expert on this, Sandra Arndt in Brussels did this, and she's kind of my go-to person for this kind of work, using various input parameters. So the geochemistry of the pore waters and the sediments, the sediment age, sedimentation rates, and then assuming certain amounts and reactivities of organic matter input, you can basically try to build up the sediment sequence using a range of input parameters. And what in the end you want to model is the current sediment and pore water geochemistry you see. And if you're lucky, that is only possible with one paleo-environmental scenario. And the way you can read this plot here is from the top to bottom. You have a system where you have a certain TOC input, you have certain sulfate concentration and a certain degree of sulfate depletion. Now you're building up your sedimentary sequence. And in the third line here, where the red arrow is, you see TOC really peaks and sulfate gets depleted. Now, that means we must have had a high productivity event during this time. And this was coincidentally roughly around the Pliocene-Pleistocene transition. And that leads to sulfate depletion. And then you go further down the line and you look at the TOC profile, you see this peak isn't there anymore. It's almost completely degraded. But you can only explain the sulfate profile you have at present if you envision this input, this past input of reactive organic matter that is now completely degraded. So it's kind of a ghost signal that the pore water kind of preserves. So yeah, really, this reaction transport modeling gives you insights in the development of the sediment and pore water geochemistry over time, and can even reproduce signals that you might not have had preserved at all. Yeah, and that kind of brings me to the end of my talk, just a few take-home points, really. So yeah, early diagenetic processes happen in all aquatic sediments, mostly microbial or catalyzed, some rather inorganic. But you mostly generate strong diagenetic signals with changes in the deposition environment. Background sedimentation rate, input of organic matter, water column chemistry. So in a way, to be honest, if you're thinking, for example, about oceanic anoxic events that affect large parts of the ocean, they should also generate oceanic, like global diagenetic events or layers. Yeah, and pore water analysis can help us to understand diagenetic patterns, certainly in modern aquatic sediments. And this knowledge can at least partly be used to understand and explain the diagenetic overprint in lithified sedimentary rocks. From case to case, it works better, it works worse, but it's always something that's worth considering, I guess. And yeah, that brings me to my acknowledgements. I don't read them out, just the last one, because I think yesterday was International Women's Day. So it shouldn't go amiss to thank my wife. because yeah, she's always supported me in my scientific career, and I wouldn't be where I am today without her. Thanks very much.